So in motor, this induced voltage, okay, it is not called E0, but it is called CEMF. In generator, we use E0, right? The induced voltage. But in motor, they are called counter electromotive. But the concept similar to E0 in generator. Okay? Why it is called counter electromotive force? Because the polarity act against the voltage source. Okay? So from here, you supply, okay, from here, connect to battery, for example, the source. Then you supply current to the armature. So the coil, okay, now coil carrying current in the magnetic field subjected to Lorentz force. Okay, so you would cause this armature to rotate. So when the armature rotates, at the same time, you will cut the flux. So when you cut the flux, you will induce voltage, which is E0. But this is motor. So we don't call it E0, but we call it CEMF. Follow? Okay, the counter electromotive force. Why counter? Because the polarity of this E0 now, the CEMF, now is called CEMF, counter electromotive force. So, but how to calculate this E0 is same as the generator. Okay, so this CEMF, the counter electromotive force, the polarity against this source. Okay, so now, okay, this one is applied in this polarity. Okay, this one, the CMF again this one. So the net voltage in the circuit is ES minus E0 is the CEMF. Okay. So this is the net voltage, okay, in the circuit now. So acceleration of the motor. So the net voltage in the circuit is this. Okay, this is the CEMF. It induced due to the generator effect. So now, okay, the current here, I, current that is supplied to the armature here, is equal to ES minus E0 divided by R. It's not ES divided by R, but ES minus E0, because not net voltage now reduced because this E0 opposed. Okay, okay. So this is the current that is supplied to the armature. So when the motor at rest, it means not yet rotate now. Okay. So when the motor at rest, of course E0 zero, right? Because E0 only when the conductor cut the flux. So when at rest, E0 is zero. So that's why we have I equal to ES plus. But this is the starting current. So this is the starting current because this is at rest. But when it starts to rotate, the IR, which one bigger you think? Top or bottom? Bottom. So the starting current is bigger or bottom. Okay? Because at start, armature not yet rotate, right? So E not zero. So but when it starts to rotate, there is CEMF. Okay, the generator effect, the counter electromotive force. So the current will start to reduce. Okay. Okay. So up to now, okay. So the starting current may be 20 or 30 times greater than the nominal full load current of the motor. So concept full load, no load, same. For motor, no load means not connected to any devices, just open. Okay. But full load, it gives maximum power that it can supply. Okay, meaning it have to rotate very big thing lah. Maximum power that it can supply. No load, it rotate freely. That's motor. Okay, motor. At the shaft, you connect to something like if they want to rotate. So in practice, this would cause the fuse to blow or the current breaker to trip. So if the fuse absent, large force acting on the armature conductor produce a powerful starting stop, okay, consequently rapid acceleration of the armature. So the starting current is very high. Okay. Okay, as the speed increase, as the speed increase, the counter electromotive force, the E0 here, also increase, right? Because E0 is Z flux over this, right? So when speed increase, of course E0 will increase. So when E0 increase, the net voltage will decrease, right? When net voltage decrease, what happens to the current? Current drop. Okay, the armature current drop. So the armature current drop progressively as the speed increase. Okay. Although the armature current decrease, motor continue to accelerate until it reaches maximum speed. So at no load, speed produced by CEMF, okay, slightly less than the source voltage. Okay, at no load, this speed produce. Okay, so at no load, so maybe you don't have to take it, just take it. At no load, the E0 slightly less than E. Okay, at no load. So no load, E0 slightly less than E. May not connected to any load. Okay, so if E0 equal to ES, okay, later no problem. Later you read it again, and then step by step you will understand. So if E0 equal to ES, what happens to the net voltage? Become 0. So when net voltage 0, current will also become 0 because current is this divided by R. So since current becomes 0, the driving force will stop to act on the conductors. So the mechanical drag imposed by the fan and bearing will immediately cause the motor to slow down. Okay, so the idea here is when E0, okay, because you give this armature rotate, right? Okay, so when the induced voltage in this armature, okay, equal to ES, equal to the because it's rotate fast. So at that time, the I becomes 0. When I becomes 0, there is no current supply. So motor slow down, stop. But motor not stop drastic. It start to slow down. Even though no current, but it takes some time to properly stop. Even though there is no current, because you just imagine when motor rotate with some speed, even though you cut off the current, but it takes some time to really stop. Okay? So motor start to slow down. So as the speed decrease, okay, that one when speed increase. So as the speed decrease, net voltage increase. Why net voltage increase when speed decrease? Yeah, because E0 now decrease. Okay, this one speed increase. Speed increase, E0 increase. Okay, when E0 increase until E0 almost almost same as the ES. When same as the ES, net voltage becomes 0, so current becomes 0. So start to okay. And then as speed decrease, this one decrease, so net voltage increase. So when net voltage increase, current increase. So speed will stop. Okay, this is decrease, so speed at this one increase. Okay, when speed increase, motor accelerate until reach maximum speed. Okay, maximum speed is when the E0 almost same as F. Okay, this one speed decrease. Speed decrease, of course the end should be stopped, right? Okay, but when speed decrease, okay, you understand this. Speed will start to fall as soon as the torque developed by the armature current equal to the load torque. Okay, so when the motor runs at no load, the counter EMF must be slightly less than ES, so as to enable small current to flow, sufficient to produce the required torque to keep the motor rotating. Okay, I think what you need to do is you read this slide, and this slide again, and then you relate with this equation and also the equation of. Okay, so the example here, permanent magnet. Okay, this generator has resistance of 1 ohm and generate voltage 50 volt when speed 500. So this DC generator induce voltage 50 volt when speed equal to this. Armature resistance 1. This armature connected to. Okay, so the because machine, they can act as motor and also as generator. So this is permanent magnet. Permanent magnet, the circuit is very simple. Here is the armature. There is no other circuit because this one comes from the permanent magnet. Okay. And then this one 50 volt, the E0. So E0 equal to 50 volt when it acts as generator. When the speed of this is 1 ohm. When speed rotation here is 500 RPM. At 500 RPM. Okay, so this generator. So now, to the same machine, okay, you connect to a source, 150 volt. So now, we act as a motor, right? To supply. Okay. So, calculate the starting current, the counter EMF when the motor runs at 1000 RPM and at 1460 RPM. Armature current at 1000 RPM and at 1460. Okay, starting current. What's the starting current? Huh? Starting current. Starting current. Starting current E not equal to what? Zero lah, because not yet started, right? So 150 lah, because 1 ohm only here, right? Okay, so starting current is 150. I don't want to test your mathematics, just to understand the concept here. So because E0 is 0 starting, and then, so starting current is 150 ampere. So when this armature receives 150 ampere, is subjected to Lorentz force, right? Because they are in the conductor. Suppose they are so it starts to rotate lah. It starts to rotate. So when it rotates, it will produce CEMF, right? The generator effect. Okay. So calculate the CEMF when motor runs at 1000 and also 1460. Okay, so the E0 is Z. What's the relationship between E0 and speed? Directly proportional. Of course, Z we don't keep changing, so we assume this is constant. Now, and a permanent magnet. So this one is constant. So directly proportional. So at 500 RPM, it induced 50 volt. So at 1000 RPM, it would induce how many volt? 100. Okay, 100 would double. At 1460 RPM, it will induce 146. Okay, just to understand the concept only. So, E0 induced here. So when E0 induced, what happened to the net voltage? Decrease, right? Because supply voltage 150 volt need to minus this induced voltage in the armature due to the generated effect, which act opposite. Okay, which act against this one, the supply voltage. So the armature current at 1000 and 1460 decrease or increase? Decrease lah. So can you calculate this one? At 1000, it's 50, right? So at 1000, 50 lah, correct? And then at 1460, 4 ampere. And can you follow? No, it's not an example to test the mathematics, just to understand the concept, what happened from the starting, and then when it starts to rotate, what happened to the armature current, okay, the voltage induced in the armature. Okay, so starting current 140, so when it starts to rotate, okay, you see when the motor, the speed increase, this one speed increase lah. Okay, 1000, 4000. This one up to here is nothing to do with this. What's the information given here? Only this one, but nothing to do with this problem. Correct or wrong? Because this problem is for motor. This one up to here is only to show that the relationship between. Okay, that's all. Okay, so the circuit similar to generator. I don't want you to memorize. Okay, if let's say you want to draw for shunt motor, same thing, you draw the armature. The field parallel. So this is for generator, this is the terminal, right? So now this is the supply voltage. So the supply voltage lah, because motor need supply voltage. And then the armature current in or go out? Go in lah. Now motor they need current. If generator go out from the armature. This one still the same lah, because the field is still in the exciting current. Okay, the field current. And what about this one? Enough, right? Supply, start to supply. Okay, this is called line current. In generator, we call it load current, because supply to the load. This one comes from the line. Okay, so this is IL, this IA, this is I. So same thing, concept same here. We apply KCL here. If you compare to this one, also same. This is the line current, armature current, and it is the field current of circuit. And then this equation, just a simple Ohm's law, simple KCL and KVL. You don't have to go through this, okay, because you have learned this before. So similarly for series motor, for compound, same thing, exactly same. Just the direction of current now different from the other. Okay, so now we do example. 220 volt. This is the rating voltage. Shunt machine. Machine can be generator, can be motor. Okay, it can work because machine, the construction exactly the same. Just if you supply mechanical power, it works as a generator. If you supply electrical power, it works as a motor. The construction same. So armature resistance 0.5, full load armature current 20 ampere. Find the induced EMF, the E naught lah in this case. Okay, when the machine acts as a generator and acts as a motor. So generator is E naught, motor also E naught, but it's counter. Counter because of the direction is opposite. Not the polarity is opposing the that's what it's called counter. Okay, can you calculate? So you draw for the shunt machine, you draw the this one. Armature resistance 0.1. This is 220 volt because the rating voltage for this machine is 220 volt. So it works at a 220. Full load armature current. Okay, armature current. So depends. Now you want to generator first. Generator armature current out or in? Go up or go apa ni? Downward or upward? Upward lah. Okay, for generator is okay. Other information not given, but is it enough to calculate enough? Enough or not to calculate enough? Because it's very simple. Enough, right? Because we need to calculate the voltage drop here. Voltage drop, and then you obtain E naught. So E naught, when it acts as a generator, E naught equal to what? 22 plus or minus? Plus 20 times 0.5, right? Okay, when it acts as a motor, going down or going up? Going down lah, because they need current. Okay, armature need current to rotate. Okay, because now the machine acts as a motor. So E naught equal to what? 220 . difference? Same circuit. This one supply. Okay, because it generate. This one consume. Okay, this one generate. Okay, because motor they consume electrical power and convert to mechanical. But for generator, it take mechanical power and produce electrical power. Okay, so for generator, the E0 greater or less than 2020? Greater, right? Some loss here, so power at the terminal less than induced in the armature. But for motor, E0 less or less, right? Because the supply is 220, loss here, and then really used by the armature only this. Okay, because of the loss. Okay, so basically what I want you to understand is the difference between generator and motor. It is opposite because the operating principle is opposite. The construction same, but operating principle opposite. Very simple. And then for this example, just to understand, okay, the starting current and what happens when the speed start to increasing. Okay, because this one from the this all the sentence is speed increase. This one the example when. And then if you increase some more at one time, E0 okay, equal to ES, right? The maximum speed. So when E0 equal to ES, what happen? 0 volt lah. So start to. Okay, that's for now lah, the starting. Later you when as we discuss this thing, we go more, okay, we discuss further, then you will understand. That's for now. Okay, so next is okay, mechanical power and torque. These two are the most important properties for motor. When we discuss generator, this torque not appear, right? Okay, but now we discuss motor. And this is the equation for induced voltage due to generator effect, which is C and F for lap winding. Okay, we familiar with this. For wave winding, what is wave winding? We need the multiply the P over A. Okay, we discuss last class. Okay, so here, okay, we use same motor here, simple circuit, permanent magnet motor here. The power, the electrical power supplied to the armature, okay, equal to the ES multiplied I. This is the supply power, okay, to the armature. And then previously we have this, right? Correct? So this, when you write this is same, right? Okay. So ES is E0. This is when motor start to rotate, and when E0 start to induce, plus IR. So when motor start to rotate, the ES here Go to this. Strap. Okay, when there is E naught now. And then we can write this one. Okay, so this is the power loss here, and this is the power that is converted to mechanical. This is the power supply. Power supply is all, but there is some power loss here, and this is the power that is converted to mechanical power. Okay, this is the power loss, and this is the power that is converted to supply power. Supply power is AES multiplied I. But converted to mechanical power only this one. This one lost into the armature. So the mechanical power of the motor is equal to this. Because this is the electrical power that is converted to mechanical power. So this is for the mechanical power of the okay. So now we consider 20 kilowatt rating power, rating voltage, shunt, armature resistance 006, field resistance 100. Determine total armature power developed when working as generator deliver 25 kilowatt and motor KIE2009. So you draw here shunt. This is 0.06, there is 100. Okay, generator. Generator deliver 25 kilowatt. This is terminal lah, this generator, this is terminal. Okay, so this is IA. Working at wood, okay. This is of course in this direction lah, because it takes exciting current. Okay, for generator, load current is in this direction. So what is load current here? 35 divided by full load current, maximum load current that this generator can supply. Is 25 kilowatt divided by 250, so equal to 100. So this is the full load current, maximum current this generator can supply. Okay, can you calculate? So what is next? IX. So what is IX? IX equal to? IX 150. Okay, so 2.5. So what about IA? Can we calculate IA? Here the question is determine total armature power. So power developed here. Power developed in the armature. So to calculate power developed in the armature, you need IA and E naught, right? So can you calculate IA, and after IA can you calculate E naught? Can, right? You calculate IA, you use KCL here. Then you can calculate E naught. You consider the KVL at this. Okay? So this is generator. So now if motor IX still same or opposite? Same, right? Same lah. This still needs exciting current. What about IL now? When motor? Line current. right, the direction. What about IA? Also opposite lah. So now motor, they need electrical power. So same thing, IX same, but IL, is it same now, the line current? Is it same? Is it same line current? If it acts as a motor, taking 25 kilowatt. The rating voltage for this motor is 200. Still same. Okay? Because 25k divided by 250. What about IA? Is it same? Is it same now, IA? The blue one, is it same with the red one? No lah, because now IA is IL minus IX. Right. The red one, IA is IX plus IL, right? So these two are different now. Red is the generator, blue is the motor. Once you have your IA, can you calculate your E0? E0 for motor is the CEMF, the counter the motor. But can you calculate? Can, right? Using the KVL here. So once you have your IA, you have your E0. Depends. E0 is the induced voltage or EMF, or the CEMF. Depends on. Depends you work as a motor or as a generator. But the concept still the same. Just polarity opposite. So can you calculate for both? Okay, so that's why the calculation is simple, but you need to understand what information given, okay, and what parameter you need to find. And you know, apa ni, circuit for, because circuit is very simple. Circuit is very simple. So that's why for this subject, calculation, I don't worry at all. It's very simple calculation. Okay? If you compare this circuit with the circuit that you learn in circuit analysis 1, very much different, right? Circuit analysis 1 much more complex. This is a simple circuit. Simple KCL, simple KVL. And the circuit is fixed. For each type of motor or generator, fixed. Okay, so what's the answer? Give me the answer for P generator and also P motor. When they work as generator, what is the power developed here at the armature, and also when it work as a motor, what is the mechanical power developed in this. Any answer? What's your answer? Make sure that the answer given here. answer. PA is okay as generator 26255 watt. Correct. For motor 23805. Roughly lah, if your answer about the same close to this answer, then correct lah. Because sometimes we take 2 decimal point, sometimes take 1 decimal point, right? Okay. But most important, it's not the mathematics, the calculation, but you know how to use the information given. You understand the situation. Okay? And then this one you can try. Okay? We'll discuss class. Okay, so I think that's all I have class. Okay, you can try this one. This Shanmoto. This one also very simple. Okay, mechanical power developed by the motor. How to calculate this? What is mechanical power developed by the motor? Yes, the power at the armature. Okay, not the power that you supply. Because power that you supply, there must be some losses. Okay, so the power that is converted to mechanical power is actually what the induced, the CMF, the E0 multiply the armature. Okay, so that's all. Can I have the attendance back?